Hello, class. This is a recorded lecture for section 6.6, which is solving log and exponential functions using properties of logs, as you will see. And so this is sort of the culmination of this idea of exponential functions and the introduction of the inverse, which are the log functions, and using them to solve these equations. So let's get started by just walking through a bunch of examples. So what I did here is I put the properties that we're going to be using to do these solutions. And the first thing I'd like to talk about is where the log function becomes super critical. And to me, this is it right here. And I think I had this problem up on the board before. Back in the original sections of exponential. How do you solve this? How do you solve this if you can't match the bases? You can't. You just be guessing and checking, and you get really close, but you're not going to get an exact solution. But the last property down here, this is the power property, where if we take the log of both sides, and I'm going to use natural log because I noticed in my math lab, they seem to use natural log as well, but you could use log base 10 as well, right? So let's take the natural log of both sides. So now what happens? Now we could use the power rule property of logs, and guess what? We can bring the x out, and now you see we can do some normal algebra. And the beauty of this is, remember, log of 20 is just a number. So if you divide both sides by log of 3, natural log of 3, excuse me, you would get x equals natural log of 20 over natural log of 3. And even back in the day, before the fancy calculators did have log functions. So you just get it out and do the arithmetic with regards to the calculator, and you would see you would get a number 2.727, etc. And so this is, in my opinion, I know mathematicians would cringe when I say this. This is why logs were invented, to solve equations like this. See, because if we have an equation, let's see here. Sorry about that. There's going to be a lot of erasing in this one. But if we had an equation that we originally started with that looked like this, right? 2 to the 5th equals 64, right? We could solve that. Whoops. I gave you the answer. 2 to the x equals 64. Remember, we solved that originally by making this 2 to the 5th and this 2 to the x. And you set these equal to one another, and you can see x equals 5. But you can see in the real world applications, that doesn't show up all the time. So really, that is a critical, that last property there, the power rule property as it's called. And you'll see that when we do the application sections, talking about money, talking about growth rate, etc., we're going to be using that property pretty much exclusively. But with that, we do have some other log equations to introduce you to and how to solve those. So let's start with one that's reasonably simple. Say like we have log of 4, and then we have x equals 2. So how do you solve this one? Well, when you have a single log equals a number, right? How do we solve it? Well, the key is to use the inverse property, right? The first property, the idea that we can convert this to an exponential. And so if you do that, right, x comes out. 4, this value here is our y, so that would be squared, and you would get x equals 16. So when you get used to logs, you probably could see that and figure it out just by looking at it. But with regards to more complicated ones, that will be the strategy. What's really nice if you had something like this. And don't let these two, say like you had log a base 4 of 6. So now you have a log equals a log, right? And so again, by the equality properties, when you have something like that, the bases are the same, the logs are the same. What does x have to be? It has to be 6. So that would be another possible way to do these solution sets. So if you have a log equals a number, you use the inverse property and convert it to an exponential. If you have one log equals another log, then you put them on different sides of the equal sign, right? And then the arguments are equal. So what do we mean by that? Let's see here. If we do, let's do one more here by, so let's continue by looking at this equation here. And this equation is a log on one side equals a log of the other. So now we can combine the arguments. But before we do that, we have to make sure all the numbers are inside as well. So here we have this -2 out front. So the strategy would be bring the -2 inside, the log on the left side of the equal sign. Now we could set the arguments equal to one another. So that would be x to the -2 equals 9. How do we solve this? Well, the strategy is we want to do something to both sides of the equal sign where we have x equals something, right? So how do we get rid of the -2? Well, we want to have that equal to a 1. So what we do is we multiply each side by minus, or take it to exponent of -1/2. So what do we do here? -2 times 1 -1/2 equals x. And now we have this 9 to the -1/2 power. Remember, this would look like 1/9 to the 1/2 power. And what is 1/2? Square root. So that would equal 1/3. So you can see this is starting to get a little bit tricky. You got laws of exponents, you got logs or properties of logs, and all these ideas that come in play with regards to these calculations. So again, the two strategies, right? If you have if you could have one log equals another log, the beauty of that is then the arguments are equal, as we're doing in the last couple examples. And then if you have a log equals a number, you use property number 1 to convert it back to an exponential. Okay, so here's another equation. Now we have 2 logs that equals a number. So you remember the strategy when we have a number, what we want to do is we want to have a single log and the number, and then use the top property there, the inverse property, to convert it to an exponential. Well, we have 2 logs. Well, let's combine them, right? And so we could use here the multiplication property, where m would be the x and the n would be the x plus 3. And so we can combine those. It would be log of x times x plus 3. So now we have a single log, right? Equals 1. So now we want to convert it to an exponential. How do we do that? Property number 1. And remember, when there's no number here, that's base 10. So you would have x over x plus 3 equals 10 to the 1 power. So if we expand this out, you get x squared plus 3x equals 10. I thought you were probably hoping you were done with quadratics, but no such luck. Remember how to solve them, right? Bring the 10 to the other side and set it equal to 0, and use either the quadratic formula or you could factor it. My nice math class here, we can factor this. It would be x plus 5 and x minus 2. And so our 2 solution sets is x equals -5 or x equals 2. So when you do these calculations, you'll always have to double check and make sure that these both work. Usually, my experience is one of them works and one of them doesn't. And you can see right away that the -5 isn't going to work. Here's what I mean by that. When you plug that in, you get log of -5, and you don't even have to plug anything else in. You can't take a log of a negative number, right? Isn't going to work. So you can get rid of that right away. And we could say this one, whoops. This one here does not work. But let's try the 2. So you would have log of 2 plus log of 2 plus 3 equals 1. So this is log of 2 plus log of 5 equals 1. So by the product rule property, you can multiply those together. Log of 2 times 5 equals 1. And just to finish that, this would be log of 10 equals 1, and that is true. You could use your calculator, but remember, this is base 10, and the argument is the base are always equal to 1. So here is going to be, I think, our last example. And so here we have 3 logs, right? And now I just used the natural log to give you another feel for a different base. But strategy is now, since there's no constants anywhere, you want 1 log on one side of equal sign, 1 log on the other, and set the arguments of each log equal to one another. So what do? Well, let's combine the log that we have on the left side using the quotient rule. And so this would be log of 4x plus 6 divided by x plus 5. And that would be natural log of x. So now you have logs with the same base. So this has to equal x. So now we can do regular algebra on it. Equals x. So what do? Multiply each side by x plus 5, right? So these two cancel. And this would be 4x plus 6 equals x squared plus 5x. If I multiply these through, guess what? Another quadratic. How do we solve this? Well, same way. Bring everything to one side of the equal sign, bring the 4 over. 4 minus 5 is plus x. And then we have the minus, this plus 6 turns into minus 6 when we bring it to the other side. And again, strategically set up where we could factor it. So we have x equals minus 3 or x equals 2. You got to check them. And so to do that, you plug it into the equation. And I need a little space here. So let me erase this part here. And so when we plug it into the equation, we start with minus 3, and you'll see right away that 4 minus 3 plus 6, that would be natural log of minus 6. That does not work, so we could not have to worry about the minus 3. We hope minus 2 actually works. So it'd be 4 times 2 plus 6 minus natural log of 2 plus 5 equals natural log of 5. Let's see what happens. So we have natural log of, this is 8, so this would be 14. All right. All right, and then not 5. Why did I plug 5 in? No idea. Okay, x is 2, so we will plug 2 in here. Thinking, how are we going to get 5 with 14, right? Because I put the wrong number in. So when you plug 2 in, this would be natural log of 7 equals natural log of 2. And now we could use the quotient rule again, right? Natural log 14 divided by 7. And you see that equals natural log of 2. And does that equal natural log of 2? Yes, it does. And so we proved that the one answer doesn't work. Whoops. One answer doesn't work, and the x equals 2 does work. So those are examples. We could continue to do some more, but I'm going to end the lecture for section 6.5 with, or 6.6, excuse me, section 6.6 with that last example.